Welcome to Air Tightening Your Home, the fourth program in our 5-part series on building an energy-efficient home in the Southeast. I'm Bruce Dweck, Chief of the Energy Conservation Division of the Jacksonville Electric Authority in Jacksonville, Florida. This series was designed to help you plan, build, and equip your home so that the most energy-efficient features are included for the most cost-effective approach. The ideal time to include energy-saving features is during the planning stage of construction. Most energy features left out or not considered during this time usually cannot be added later at reasonable cost. To determine what energy features should be included, climate must be considered. In fact, what is an excellent construction practice in Chicago could actually be detrimental here in the hot, humid South. All of the information in this series applies to the area shown in green on this map, comprised mainly of the state of Florida and the Gulf Coast regions of the United States. We'll begin this program with vapor barriers. The location of a vapor barrier is important because placing one in the wrong location could cause moisture damage to the walls. Once we've heard the experts answer the question about vapor barriers, we'll finish the subject of air tightening frame buildings. You'll also see how to meet the same goals with masonry construction. Moisture control and indoor air quality will be dealt with as well. Let's get started with vapor barriers.
A vapor barrier is a material such as polyethylene that inhibits the travel of moisture. Vapor barriers are used under slabs and often in walls to prevent unwanted moisture from traveling into the house. For cold climate areas, experts recommend that vapor barriers be located near the inside surface of the wall. But in the hot, humid climate of the Gulf Coast region, shown in green, placing a vapor barrier near the inside surface of the walls can actually cause moisture damage to the wall. The foremost experts on vapor barriers are the American Society of Heating, Refrigerating, and Air Conditioning Engineers, called ASHRAE, and the United States Department of Agriculture, or USDA, Forest Products Laboratory. These two organizations came to the same conclusion published by ASHRAE. In humid climates, exterior surfaces of the building should have higher vapor resistance than interior surfaces. Where vapor barriers are used, they should be on the outside. Note that this is the reverse of the recommended practice for cold climates. Gerald Sherwood is the engineer who directed vapor barrier research for the USDA Forest Products Laboratory. Mr. Sherwood explains the results of these studies.
The ASHRAE map shows the hot, humid climate in green, and in that entire green area, vapor barriers should not be used on the inside face of walls. The Forest Products Lab conducted studies of vapor barrier placement in buildings, in test buildings in Gulfport, Mississippi, and Beaumont, Texas. These studies by the Forest Products Lab are the most extensive studies to date. The USDA Forest Products Laboratory studies do support the ASHRAE position for placement of vapor barriers in the hot, humid climate. If the vapor barrier is located on the inside surface, there is a greater tendency to cause condensation in the summer, and therefore it could encourage decay. The greatest likelihood of biological action in the walls would occur during the summer when the temperatures are high. Decay does not grow at temperatures below 40 Fahrenheit, and it grows progressively faster as temperatures are warmer. Therefore, decay could be a hazard if condensation occurs during the summer on vapor barriers that are placed near the inside face of the walls. In some of the areas in the hot, humid climate area, cold conditions do exist in winter that could cause condensation. However, these periods of cold are usually quite brief, it's expected that even though they might present conditions that could cause condensation, that the materials in the wall will probably absorb the moisture for that brief time, which would not cause any damage. An appropriate method of addressing the vapor barrier and air barrier issues for frame dwellings in hot, humid climates is to place a foam board sheathing on the exterior of the frame and then air tighten it using tapes and sealants. There would be no interior vapor barrier, and the exterior vapor barrier would be incorporated into the sheathing. This should be a very good strategy for controlling moisture and keeping the walls dry.
Because vapor barriers must be located on the exterior side of the wall when used at all in this climate, air tightening a house by using a well-sealed foam board sheathing is ideal. Tape all seams, holes, and tears to stop air leakage. Also, seal the sheathing to both the top plate of the wall and to the foundation wall with an acoustical sealant. All air tightening methods for walls recommended in this series support the vapor barrier recommendations for walls of both ASHRAE and the USDA Forest Products Laboratory. After air tightening the walls, the next step is to air tighten the ceiling. Although the drywall material or gypsum board itself is airtight, air leakage can occur at cracks, seams, and penetrations or through holes in the top plates. Pipes, light fixtures, and exhaust fans penetrate the drywall, creating opportunities for air leakage. The best material to use when sealing around register boxes is a water-based acoustical sealant. The register box will then be sealed to the ceiling drywall. Exhaust fans are sealed to the drywall in the same manner. Seal all wire and pipe penetrations. A foam caulk is being used here. Recessed lights create another path for air leakage. If used, select the type that can operate while covered by unfaced mineral insulation. These are called insulation cover fixtures. Instead of recessed lights, track lighting can be used. Track lighting does not penetrate the ceiling. One area of air leakage through the ceiling remains to be sealed, the gaps between the top plates of walls and the drywall of the ceiling. Failure to seal these gaps allows air to leak between the house and the attic. To prevent air leakage, attach the drywall as usual, but near non-load-bearing walls, leave a distance of 12 to 15 inches in which there are no nails or screws. Then fasten the drywall to the walls using drywall clips. In this way, the edge of the ceiling drywall is attached to the walls, not to the trusses, so that if future weather conditions cause the ceiling trusses to bow, the drywall will not pull away from the top plate of the wall. And since the drywall can flex slightly, the seal will not be broken. After fastening the drywall, seal it to the top plates of all the walls. Water-based acoustical sealant is recommended for this seal. Remember, when employing air tightening techniques for the ceiling, you want to stop air leaking into or out of the conditioned living space. So, air tighten only the ceilings that are to be insulated. Air leakage in homes is not restricted to the walls and ceilings. Fireplaces are also a major source of air leakage. 12 to 25% of a home's air leakage is caused by the fireplace. Although fireplaces are very popular, they are not very economical for this area, costing 3 to 4 times as much as a heat pump to heat a home. In addition, it may be unsafe to use a fireplace when heating is needed most. Nearly 80% of the heating needs occur at night when family members are often asleep and unable to tend the fire. Fireplaces are not effective heating systems, although many people choose to include them in their homes. How can these troublesome air leakage problems be reduced? Ventilation holes are needed to circulate air through a cooling channel surrounding the flue when a fire is burning. The sunlight coming through these ventilation holes means that the cooling channel is always open to the outside, allowing air to leak into and out of the home. The solution? A double-walled flue can be used, but only if the fireplace is directly against an outside wall and if the wall between the flue and the living space is sealed and insulated. If this is done, the vents cannot draw air from the living space. If the fireplace is surrounded by living space, a triple-walled flue without vents should be used. In a triple-walled flue, cooling air for the flue is drawn from outside the house. In all cases, make sure there is a fire stop. Insulate above the fire stop with unfaced mineral insulation. Of course, a fireplace should have a tight-fitting flue damper, glass doors, and an outside source of combustion air. Air from the outside enters through a vent to provide oxygen for the fire. By using outside air, inside air which has already been heated at a cost to the homeowner does not have to be used for the fire's source of oxygen. Although fireplaces are very appealing, they can be very costly. Masonry walls constructed of load-bearing brick or concrete block are among the most frequent wall construction types in this climate area. Load-bearing brick and concrete block walls support the weight of the roof and upper floors. Load-bearing brick, such as this Norwegian brick, is heavier and stronger than the smaller brick used in brick veneer. Brick veneer is only a facing and relies on a wood frame wall to support the roof and any upper floors. Since masonry construction differs so greatly from wood frame construction, different insulating and air tightening methods must be used. The most effective method of insulating and air tightening masonry walls uses the insulation itself as the air barrier. This demonstration on a load-bearing brick wall applies to concrete block walls as well. Brick walls tend to leak water during wind-driven rains. While laying the course of brick nearest the slab, the mason should create weep holes every 2 feet. Weep holes allow water which may leak in to drain to the outside. After the wall has been completed, a waterproofing membrane made of high-density polyethylene is installed on the inside surface of the brick or block. Furring strips are attached. Treated 1x4s were selected in this case because the wider boards accept a greater number of nails and screws without splitting. After the base strip is installed, the waterproofing membrane is sealed to the brick at the bottom of the wall. In this way, leakage water is directed to the weep holes to drain to the outside. Later, you can insert stainless steel screen or other barriers into the weep holes from the outside to prevent insects from entering the home through the weep holes. This waterproofing technique keeps the wood and carpet dry and prevents mildew. Seal the window framing to the waterproofing membrane with acoustical sealant. After the wiring is in place, the insulation can be installed. First, apply adhesive to the furring strips. Note here that there is no horizontal furring strip at the top of the wall. Most building codes require a continuous horizontal furring strip at the top to meet fire stop requirements. Next, fit the insulation board into place. In this case, the insulation is 1.5-inch phenolic foam with a total R value of 12.5. The insulation board has a reflective foil on both sides. The more reflective side, the side with less lettering, should face the outside of the building, where there is a 3/4-inch airspace created by the furring strips. Whenever a reflective surface faces an airspace, it creates a partial barrier to heat flow. Note that the nails have heads which won't break the protective foil and paper cover on the insulation board. Tape all joints between insulation panels. All joints and seams in the insulation board need to be sealed. Oil-based acoustical sealant forms an exceptional seal, but can be scraped off accidentally when the drywall is installed. To avoid this problem, gaps have been intentionally created between the insulation board and the window framing and the special airtight electrical boxes. Now the seals are recessed where they cannot be scraped off. The insulation board is then sealed to the slab. The gap intentionally left at the bottom of the wall could be a major source of air leakage and has to be sealed. An acoustical sealant is applied after a backer rod has been inserted. Backer rod and acoustical sealant are used in this case because the seal at the slab has to be flexible. In this case, interior walls have only a single top plate, so the ceiling drywall can reach from room to room without being cut. This eliminates the need to seal the drywall to the interior walls when air tightening the ceiling. A gap was intentionally created between the ceiling board and the wall insulation board to protect the seal in this location. The final step in air tightening masonry walls is to seal this gap. Again, water-based acoustical sealant is recommended. The techniques recommended for air tightening and insulating load-bearing brick walls also work very well for concrete block. Air tightening the home during construction is one of the major passive features of an energy-efficient home in the hot, humid Southeast. Air tightening reduces air conditioning needs by reducing the amount of warm air and moisture that can enter the home. On a typical summer day, 9 to 10 gallons of moisture are carried into the home by air leakage. Once construction has been completed, the opportunity to reduce this amount of incoming moisture by air tightening will not be available again. It is also important to control moisture released by the activities of the people in the home. On the average, the occupants of the home can cause 2.5 to 3 gallons of moisture to be released into the home every day, summer and winter. Even the burning of petroleum products, such as natural gas and kerosene, releases water as a byproduct. The best way to control this moisture is to remove it immediately from the area where it is released.
Exhaust fans are very important because they remove moisture that's generated inside the house. The best fans, like this one, are of large capacity. Large capacity fans should be used in bathrooms, kitchens, and laundry rooms if the laundry room is inside the house. It should be 100 cubic feet per minute or more capacity. There should be a spring-loaded damper, like this one. It keeps air from leaking into the house and out of the house when the fan is off. It also should be quiet. This one is as quiet as a refrigerator.
The truly passive energy-saving home in this climate area should be air-tightened. However, tighter houses may be more susceptible to indoor air quality problems. Pollutants may accumulate in the home because there is not as much outside air entering to flush them out. Fortunately, many of these potential problems can be prevented by taking precautions during construction. Moisture in the home is considered an indoor air pollutant because it encourages mold and mildew growth and can worsen the effects of other air pollutants. For example, high humidity increases the rate at which formaldehyde is released from construction materials and home furnishings. To prevent moisture problems, air tighten the home and ventilate those rooms where moisture is produced. An indoor air pollutant which has received a great deal of attention recently is radon. Radon is a colorless, odorless gas which may cause lung cancer. How does radon get into the home? University of Florida researcher Charles Ressler coordinated a survey of radon in Florida homes.
Actually, there are 4 general routes, and in order of decreasing importance, they include from the ground, from domestic water, from building materials, and then way down on the list from the outside air. The predominant entry route is from the ground, probably the most common route for most of the U.S.
Houses that are off the ground with ventilated crawl spaces and airtight floors resist radon entry from the ground. If any radon is present in the ground below, it will likely be flushed out of the crawl space through the wall vents before leaking into the home. Many homes in the Southeast have concrete slab floors. For houses with slabs, the best barrier to prevent radon from entering is the concrete slab itself, if the slab is formed using 4 simple steps. Since radon can enter the house through cracks in the slab, it is important to reduce the number and the effects of cracks. The first step is to make sure that the concrete contains one of the inexpensive chemicals which help prevent cracking. The second step is to reduce the total amount of cracking. This is done by preventing water from escaping from all exposed surfaces and edges of the slab for the first 7 days. Plastic sheeting is very effective for this, and spray-on curing compounds allow construction to proceed without delay. Without the use of these water-retaining curing techniques, the concrete will shrink and crack more frequently and will achieve only about half its rated strength. Although curing the slab will reduce the number of cracks, cracking cannot be stopped entirely. The third step is to make all cracking occur in predetermined locations. This is done by intentionally forming or cutting grooves in the concrete. These grooves, called control joints, are 1 inch deep. Cracks will occur only in the control joints themselves rather than at random. The fourth step. If a problem with radon is detected, the control joints can be filled with special sealants. Without the control joints, it is impossible to seal cracks. Other pathways for radon gas are pipe penetrations through the slab. Seal all pipes to the concrete slab. Pesticides, including those for termite control, can also enter the home through the slab. So any measure to protect the family against radon will also help protect against pesticides. These and other ideas on reducing risks from radon can be found in publications of the United States Environmental Protection Agency. Formaldehyde is another indoor air pollutant. It is a strong-smelling, colorless gas that is a suspected cause of cancer. Formaldehyde is released from glues and binders used in building materials, finishes, and home furnishings. Nearly all products made with formaldehyde release it to some extent in vapor form. Of chief concern are hardwood plywoods and veneers used for wall paneling and doors, as well as medium-density particle board used for subflooring, cabinets, and countertops. Coatings of heavy sealers, such as alkyd paints, help reduce these formaldehyde emissions. Paint the backs and bottoms and all other exposed, unfinished surfaces of cabinets and vanities with such a sealer before they are installed. Of course, more expensive solid wood cabinets can be used which do not contain formaldehyde. For flooring in a multi-story house, avoid the use of particle board or interior class plywood which release more formaldehyde. Instead, use wood panels with either an exterior or an exposure 1 classification. Combustion byproducts contain many air pollutants. These pollutants can leak from gas stoves and fossil-fueled water heaters and furnaces and from wood stoves and fireplaces, even when these devices are vented properly. The U.S. Department of Energy has identified tobacco smoke as a significant air pollutant and possible cancer-causing agent. According to Department of Energy publications, smokers should smoke outside or near an open window. Often without being aware of it, homeowners use many toxic compounds around the home. Paints and adhesives, carpet and oven cleaners, cleaning fluids, floor and furniture polishes, and pesticides all release undesirable chemicals into the air. In an airtight house, extra precautions should be taken. For example, time carpet cleaning, floor waxing, or interior painting to be done during moderate weather when windows can be opened and the house ventilated. Opportunities for ventilating the home occur frequently throughout the year. In this climate area, there are 80 to 100 days a year in which there is no need to air condition or heat the home. The most effective and least costly way to control indoor air quality problems is to prevent them before they occur. To prevent problems, steps must be taken during the construction process. Of course, many indoor air quality problems, if they occur, can be corrected after construction, but at a much greater cost.
It was only a few years ago when indoor air quality was something which the average home buyer knew little or nothing about. But now, with homes being air-tightened more and more, many people are wondering, can a home be built too airtight? The answer is no. By incorporating air-tightening techniques shown in this series, the homeowner will have control over the amount of air flowing into and out of the home. Normally, airflow would be kept to a minimum to reduce utility bills. If, however, an indoor air quality problem occurs, you can temporarily increase the airflow into and out of the home. For example, if the inside of the house is being painted, you can, of course, open the windows for extra ventilation. If air tightening is ignored during construction, then you won't have control over the airflow, and your monthly utility bills will reflect this. Much of the air tightening process can only be accomplished during construction of the home. These opportunities won't be available again. In the next program of our series, we'll be covering heating and cooling systems. The cost of heating and cooling is the single biggest contribution to a home's energy bill. And the heating and cooling systems and their efficiencies and sizes will determine to a large extent how large or small your energy bills will be. Thanks for joining us for Southern Home Building Blueprint for Energy.